Okay, so this is the question about graphs. So in the first part, we are trying to prove that if a graph G is bipartite, meaning that if we can partition its vertices into two sets L and R, such that there is no edge going from a vertex in a set to another vertex in the same set, then there is no cycle of odd length. So let's try to prove this using contradiction. So we assume that what we are trying to prove is not true, meaning that there is a cycle of odd length, which I'm going to draw here. So this is a cycle of odd length that exists in our graph. Okay. So now let's see why we can get a contradiction here. So let's start with a vertex. Let's start with this vertex in the cycle. Let's assume that this is in L. Okay. The other case where it is in R is just very similar to the arguments that I'm gonna give you. So without loss of generality, we can assume that it's in L. Otherwise, you can just switch L and R or just repeat the same argument. Okay, so this vertex is in L. Now, what does that tell me about this vertex? Well, this vertex and this vertex are connected. So this vertex cannot be in L, so it has to be in R. Now that I know that this vertex is in R, this vertex has to be in L. Right? Because if it was in R, there would be an edge going from a vertex in R to a vertex in R. So this is in L. Now I can just repeat the same argument to prove that this vertex is in R, or I can go from this vertex in the reverse direction and prove that this is in R, this is in L, and so on, right? As you can see, all of the vertices that are adjacent to a vertex in L have to be in R, and all of the vertices that are adjacent to a vertex in R have to be in L. Okay, now if I repeat this, I can see that so this was my starting vertex. Every vertex that has a distance which is odd from my starting vertex is going to be in R, and every vertex that has a distance which is even starting from my starting vertex is going to be in L. So when I complete the tour around the cycle, what does that tell me about this vertex? Well, I know that my cycle is of odd length, so this vertex has to be of even distance from the starting vertex when going clockwise around the cycle. So that tells me that this vertex has to be in L, but I just proved that this has to be in R. So this is a contradiction, and we can see that there has to be no cycles of odd length. Okay, so now let's go to part 2. Okay, let's count the number of edges in our graph. For each edge, one of the endpoints has to be in L, one of the endpoints has to be in R, right? For example, this edge has one endpoint in L, has one endpoint in R. This one might have this endpoint in L, this one, and this endpoint in R. Okay? Now I'm going to prove that both sides of this equality that we are trying to prove are equal to the number of edges in the graph. Now why is that? Well, if you count the number of edges, you can assign every edge to its endpoint, which is in L. Okay? Now, how many times is each vertex gonna be assigned to edges? Well, exactly its degree. So if this vertex V is in L, then for each of the edges that are adjacent to it, it's gonna be counted one time. So this means that the sum of the degrees of vertices in L is exactly equal to the number of edges in the graph. Now, by the same argument, you can prove that if we assign each edge to its endpoint, which is in R, then you're still going to be counting the number of edges. So this is exactly equal to the sum of the degrees of vertices in R. So I've just proved that these two quantities are equal.